Well, more about electron configurations. Specifically, how exciting, right? Specifically, how do the electrons uh, orbit or place themselves into stable configurations around not just atoms but ions that have come from those atoms? This really helps to have this pattern of electron filling and electron configurations from chapter 2 set in stone in your head. That way, when I say that calcium likes to lose 2 electrons, you might imagine it likes to lose 1 and lose 2. Or if I say calcium is the 4s2 element, those 4s electrons, 4s1 and 4s2, are easily lost. Yeah. All right, let's go to something we've seen before, perhaps. Yeah, you know sodium is the 3s1 element. The electron configuration is 1s2, 2s2, 2p6, 3s1. Therefore, and you already know the answer if you're looking right below, which of these electrons, 1, 2, 3, 4, 10, 11, which of these 11 electrons will leave the sodium atom first, as it's been known to do because sodium's so reactive and only has one valence electron and wants to get rid of it. Which of those electrons will be the one to which will be the one to leave? Well, it's obvious, isn't it? I don't know, maybe it's not. It's the last electron to enter into an orbital will be the first one to leave, usually. So for the metals that like to lose electrons, they many times will lose the electrons that just finished entering into orbitals in the Aufbau scheme of things. Or I can say it's the valence electrons that they lose. Calcium is the 4s2 element, just a little bit beyond argon, the stable inner noble gas configuration of electron configuration of argon. We go argon in square brackets 4s2. So if I were to make a calcium 2 plus ion, it's the 4s electrons that leave. Sometimes I like to write the 0 up here to remind myself those 2 electrons left. But really, you wouldn't, if you didn't write this, you wouldn't know exactly, or you might not recollect what the configuration is, so you might want to write more about that than that. So another name for the argon electron configuration is neon plus 8 more electrons. Interesting. So what about strontium? Also in the calcium family. Here's the electron configuration for strontium, or krypton 5s2. It's the 5s2 element. 2 valence electrons. So guess which of those many electrons want to leave the atom first to make an ion? And strontium does like to lose 2 electrons. And indeed, it's those outer 2 electrons, the 5s electrons. So the strontium 2 plus could be written like this, or this, or this. Iron is a transition metal. So here's something really weird about transition metals. It turns out they don't lose the last electrons or the most recently added according to the Aufbau scheme, building up from smaller to bigger. They don't lose those last electrons first. They happen to lose the transition metals, and often the intertransition metals tend to lose the s orbital electrons first, and then if they lose any more, then it proceeds into the d orbitals for removal. So for example, iron, no problem. Chapter 2, Chapter 3, iron 2 plus has lost these 2 4s electrons. That's really weird. So iron has nothing in the 4s, iron 2 plus, and 6 electrons in the 3d orbitals. I guess you could draw an energy level diagram drawing the arrows. Where do they go? What removes first? Iron 3 plus also has the 4s electrons missing, plus 1 additional electron from the 3d orbitals. Zinc is very similar. Zinc is entirely full of the 4s and the 3d, but if I were to remove 2 electrons from zinc, like it likes to do, as it's been known to do, as it almost always happens, I lose these 4s orbital electrons before the 3d orbital electrons. Pretty weird. Zirconium. Here's the noble gas abbreviated electron configuration. But I wonder which of these 2 electrons will leave if zirconium wants to make a 2 plus ion. Is it the 4d electrons? No, it's the 5. This is only for transition metals do they do this. So you'll notice this zirconium 3 plus in many ways looks similar to the iron 3 plus. Not exactly, but I see a pattern. Or what about nonmetals. Nonmetals like to gain electrons. So if this is the fluorine atom electron configuration, fluorine is really close to neon in electron configuration and on the periodic table. And if it can just gain one electron, and it often does from anything it comes in contact with, it will set up an electron configuration like a noble gas, that noble gas being neon, of course, because now it has 10 electrons, still only 9 protons in the nucleus, so that doesn't change, but the electrons certainly are more stable fitting around the fluoride ion than the fluorine atom. Oxygen atoms, very reactive. Oxide ions, not so much, because if I could have 1s2, 2s2, 2p4 and gain 2 electrons to look like 2p6, then this one looks just like that one, and this electron configuration is just like this electron configuration, which is just like the neon electron configuration. Of course, this only has 8 protons and 9 protons and 10 protons, so the protons in the nucleus vary still, but the electron configuration helps determine and predict chemical reactivity and chemical behavior. Phosphorus is the neon 3s2, 3p3 element. What would the phosphide ion look like? Well, if I gain 3 electrons, I guess I'm going to add them right here, and I add them right here. So here I'm adding electrons. These ions are, remember, the negative anions are called. They get larger than the parent atom from which they came. So this would be larger than this. This would be larger than this. Oops. This will be larger than this. But the positive ions will be smaller. So this would be smaller than this, and this would be smaller than this, which is smaller than this. So if you're positive, you lost negatives, and if you lost negatives, you physically get a smaller. Here are some to practice with. If I were you, I'd pause the video and try those right now. Vanadium 3 plus, aluminum 3 plus, bromide, nitride 3 minus, sulfide 2 minus. What are the electron configurations for those? Let me scratch my head for a minute. Here are the answers. Hopefully you've paused the video already. Don't tell anybody if you haven't. Then we use those electron configurations, in some sense at least anyway, to determine or talk about more about nomenclature and naming binary compounds, say. That's another video though. I don't know why I included that here, and that's such a rehashing of something else. Alright, so practice these electron configuration for the ions. Negative ions have gained electrons, positive ions have lost electrons. Thanks guys for watching. Seriously, thank you.